Hello everyone. So today in this particular session of Module-2 Session-2 of the Discrete Mathematical Structure, we are going to start or we are going to continue discussion from the where exactly we have left with the Session 1. Right, so just to have a look back, exactly what we have went through or what exactly we have discussed in the Session 1. So I just introduced you about a mathematical induction. Fine. So while introducing the mathematical induction to you, I just gave you two good examples of a biscuit pack and of a falling dominoes. Fine. I hope you remember this, and if you remember this example, so we can clearly pop up with what exactly the mathematical induction is going to be and how exactly we are going to use with the inducting something or proving something with just a minimal element and putting the same theory across the large elements. Fine. And whenever we are going to talk about the induction or the mathematical induction, so we do need an induction principle, which I just stated. Along with this, the mathematical induction principle strongly is based upon the well-ordering principle. The well-ordering principle, again, it is going to work with the positive integers. Fine. And when I was stating about the mathematical induction principle, I just gave you these three steps or the three processes. The first one is we are going to verify for n equals 1, the first step, and we are going to assume for n equals k, and we are going to prove for n equals k plus 1. So this is what exactly we have went through in the previous session, along with few examples which we have discussed. And even I told you to discuss or try with this particular problems. So today in this session, I will take few problems from what I just gave to you, and with the hope that you have tried. If you have tried, it's good, and if you have not tried, I don't have words for that. Fine. Hence, so now let us start today's session with the problem which I gave you to try out. Hence, I'll just help you out exactly how to solve those problems in particular. Fine. Hence, the first problem let us take the first problem, that is the problem which I just gave you as the sum of n natural numbers of its squares. Hence, I am just going to have the problem as I am going to have 1 square plus 2 square plus 3 square plus so on until n equals, so this is going to be equivalent to, as you all know, it is 1 by 6. It is 1 by 6 n into n plus 1 into 2n plus 1. Fine. So this is what we are going to have. Now this is the statement what I am making. So the statement what I have been made, now this I need to prove through mathematical induction. So now what exactly this statement is going to be and how exactly we are going to prove using mathematical induction. So the three steps which I just discussed with you, that is the very first step is I need to verify. So let us verify this first, but before that, so let me make this as an open statement. So to call this as an open statement, I am just going to denote this as S of n. So let me say this as S of n. Now this is going to be an open statement for me. So now the very first step is I'm just going to see that this is going to be true for the S of n equals 1. So hence, if I'm going to say this as the first step where I'm going to have S of 1. So you know, is it true for S of 1? So for that case, I'm going to take only one element, that is 1, because n stands at 1. So this is equivalent to 1 by 6. N is replaced with 1, and this is 1 plus 1, and this is going to be 2 into 1 is 1 and plus 1. So now just try to solve this. So 1 plus 1 is 2. Now this sum ups to 2. So 2 plus 1 is 3. So 3 into 2 is 6. 6 divided by 6 is 1. Hence, so I'm going to have this as 1. So 1 square is 1, and this is going to sum up with 1. Hence, for the first condition to be verified, it is going to be true. So for S of 1 is going to be true. Hence, so S of 1 is true. So now just check out with the second statement or the second step, so which I am going to assume for S of k. I am going to assume for S of k. Hence, for S of k, I am going to have 1 square plus 2 square plus so on plus k square. In place of n, I am going to have k square. So this is equivalent to 1 by 6. In place of n, I will replace with k and k plus 1 and 2k plus 1. I am assuming to be true. I am assuming this is going to be true. So is true. Assume to be true. So with assumption, now I need to check out for, in the third step, I need to check out for S of k plus 1. So S of k plus 1. So for S of k plus 1, I am going to have this statement should be replaced with k plus 1, or I need to add k plus 1 whole square elements at the both the sides. Hence, for that reason, I am going to have 1 square plus 2 square plus so on plus k square plus k plus 1th element, and the square of this. Right? Hence, I am going to have k plus 1 square. So this is equivalent to, I am going to have 1 divided by 6. So k of k plus 1, and I'm just going to have 2k plus 1, and I need to add this k plus 1 whole square. Hence, so k plus 1 whole square. Now this is what exactly I'm going to have the statement. So now having this as the statement, now I need to simplify or solve this and see that this is going to hold good for the given statement. Hence, for that, I am just going to k plus 1 as a common factor from this side. So k plus 1 as a common factor, this whole thing should be multiplied with, I am taking k plus 1 as a common factor. Hence, I will be ending with k into 2k plus 1 and the whole thing divided by 6 plus k plus 1. This whole thing has been divided. Fine. So this is what I am going to have, or I have been simplified with. So now if I am going to solve this, again this by taking up this with the cross multiplication, I am going to again simplify this as k plus 1 and multiply this with, I am going to have this as 2k square plus k. I have just removed this bracket plus, so I need to cross multiply this 6 with k plus 1, and this is 6k plus 6, and this whole thing is divided by 6. Fine. So this is what I have been simplified with. And now just let me simplify this, and I am going to write at this part. Fine. So now this 2k square plus k plus 6k plus 6 can be written as, so k plus 1 into k plus 2 into 2k plus 3. So this can be written as 2k plus 3. So this is the form what I have written. So now this I am going to take 1 by 6 as common. Now this is going to be k plus 1 and this is going to be k plus 2 into 2k plus 3. Now this entire thing I have written as k plus 2, 2k plus 3, and this is k plus 1, and I have taken 1 by 6 at the start. And this is going to be the statement now for me. So now if I go further, if I want to just simplify, and this statement will prove enough. This statement is going to prove enough for you. Fine, that is, I am going to have n is k plus 1, and n is k plus 1 is k plus 2, and 2k plus, so this is k plus 1. So k plus 1 into 2 is 2, plus 1 is 3. Hence, I'll just make your job easier if you're not clear with this. So now, I'm going to rewrite this as 1 by 6. 1 by 6. So now this n is replaced with k plus 1. And now this n is k plus 1. Hence, I'm going to split this 2 as 1 plus 1. And now this becomes, so k plus 1 plus 1. And now this is n plus 1 is k plus 1 plus 1. And now this is going to be 2 into, so 2 into k plus 1 plus 1. Hence, now 2 into 1 is 2 plus 1 is 3. Hence, this is going to be similar to this. So now once I arrive at this statement, now I am going to say that, now this s of k plus 1, the third statement, there is s of k plus 1 is true. Hence, so s of n is true. Fine. Hence, for this, the case 1 is true now. Case 2, that is s of k assumed to be true. Hence, now I am going to have been derived this through induction, and I have said that s of k plus 1 is also true. Hence, I am going to say the statement s of n is going to be true. This is how we are going to prove something through mathematical induction. Fine. Now, I am just going to take one more problem, and I am going to even try to solve that. So, just follow these steps. Fine. The very next problem what I am going to take here is the second problem what I have just stated. That is where I am going to say phi divides. The statement what I am going to put is, so phi divides n to the power of phi minus n. This is the statement what I am making. I am just saying, so phi is going to completely divide n to the power of phi minus n. So now this is going to be a statement for me. So I'm just going to call this as a statement and denote this as s of n. S of n. So now if I'm going to the very first step, is I need to check whether this is going to hold good for the first step where I do need to verify this. Hence for that case, so let me put it over here. The very first step is the s of 1 is going to be 1 to the power of phi minus 1. Now what does this stand for? Fine. So 1 to the power of phi is 1. So minus 1 is going to give me 0, and 0 divided by phi is 0. Hence it is completely divisible or completely divides. Since we say that phi divides for the s of 1, it is going to be true. Hence we will say is true. So now the second statement or second step where I need to assume, I am going to assume with the statement s of k. Now what is s of k is going to be? Now s of k is going to be k to the power of phi minus k. Now instead of saying k to the power of phi minus k is going, or phi divides k to the power of phi minus k, I'm going to put in a different way over here. So now can I say if the phi divides a particular number, I'm going to say this, the number is multiple of phi, both are one and the same. So saying a number divides a particular number is called, also be put in a statement something like the number is multiple of phi. Hence I'm going to say k to the power of phi minus k is multiple of phi. Hence I'm going to say phi m. So m being some integer, is going to be some integer. Now whatever the positive integer from z plus I'm going to take, it should be multiple of phi for the given particular statement. Hence by assuming this is going to be true, we'll go at the next step. So where in this step I'm going to check out for s of k plus 1. I'm going to have s of k plus 1. So which is k plus 1 whole to the power of phi minus k plus 1 equals, now this should be equated to 5m. This is going to be equated to 5m. Hence, so now let us simplify this statement. So if I am going to simplify this statement, so what exactly I am going to end with? That is, I'm going to end with k to the power of 5. That's k to the power of 5 plus 5k to the power of 4. I'm going to have k to the power of 4 plus 10. I'm just trying to simplify this. Plus 10. So k to the power of cube plus 10 k to the power of square. And I'm going to have plus 5k plus 1. I'm going to have 5k plus 1. So k plus 1 whole to the power of 5. I'm going to write it as our expansion of this is going to be k to the power of 5 plus 5k to the power of 4 plus 10 k to the power of 3 plus 10 k square plus 5k plus 1. Now this is what exactly we are going to expand this. Along with this, I am going to have minus k plus 1. I am going to have minus k plus 1. So once I am going to have this, so now let me take the common factor here. I am just going to take the common factor as k to the power of 5. If I am going to take the common factor as k to the power of 5, and I am going to take minus k. I am going to take the factor from this as minus k. If I am going to have this as a common factor plus, I am just taken k to the power of 5 from this component and minus k, and I have been separated this. So now along with this, the remaining factor whatever I am going to have, that is 5k to the power of 4 plus 10 k to the power of 3 plus 10 k square plus 5k plus 2. That is so this is not going to be 2, it's going to be plus 1 here, and this is minus 1, so both will cancel each other, and I'm going to just end with 5k. So now having this, I am going to have k to the power of 5 minus k. So just take 5 as a common factor over here, and I am going to have k to the power of 4 plus 2 k to the power of 3 plus 2 k to the power of square plus k. I'm just going to have plus k over here. Fine, now this is what the statement I'm going to end with. So now I'm just going to just observe here. So k to the power of 5 minus k is going to be 5m. Hence, I'm just going to replace this particular statement with 5m. So plus, I'm just going to have this entire statement as k4 plus 2k to the power of 3 plus 2k square plus k. So now just writing one more additional step, I'm going to make this as, take 5 as common, and m plus, I'm going to have this as k to the power of 4 plus 2k cube plus 2k square and plus k. Hence, so now I'm just going to end with this particular form. Now just observe, whatever the number I'm going to get, irrespective of what is the k value is going to be, whatever the number I'm going to have, that number will always multiplied with 5. If it is always multiplied with 5, I'm sure that it is going to divide the number by 5. And for this reason, we are going to say the statement is true. The statement is true for k plus 1. Hence, it is proved. Hence, for this reason, so S of n is true statement. Now this is how exactly we are going to solve it. Now, so the two problems which I wanted to discuss with you in this session, and so I'm going to take one more example and let me try to solve that problem too. In this case, the next problem what I'm going to take, it is going to be the statement which I'm going to make the statement as, so S of n, so 1 into 2 plus 2 into 3 plus 3 into 4, so on, plus I'm going to have until the value of n, so which is going to be n into n plus 1. So this is equivalent to 1 by 3. This should be equivalent to 1 by 3, n into n plus 1 into n plus 2. Now how do I solve this? How do I solve this statement now? Right? It's again using mathematical induction. I need to say whether it's going to be true or false. So first check out for S of 1. It is going to be whether it's going to be true for S of 1 or not. So to say it is going to be true for S of 1, I am going to say S of 1 equals, just take the one statement, that is 1 into 2 is equivalent to 1 by 3, and the value of n is 1, and so 1 plus 1 is 2 and 1 plus 2 is 3. Fine. Now 3 and 3 gets cancelled. So 1 into 2 is 2, 1 into 2 is 2, hence it is proved. Hence this will stay at 2, hence it is going to be 2 equals 2. Hence this is going to be true. It is true. Fine. Hence the base statement or the very first statement to verify, it is going to be true for us. So next I am going to assume for S of k. I am going to assume it for S of k. So S of k is going to stand like 1 into 2 plus 2 into 3 plus 3 into 4 plus so on plus k into k plus 1 equals so 1 by 3 k of k plus 1 and k plus 2. This is the statement what I have been made, and is assumed to be true. So assumed to be true or assuming to be true. And so with this we'll just try to prove it with k plus 1th element. Hence, so S of k plus 1, So for S of k plus 1, I am going to have the same statement. So now what exactly I am going to add with? I need to add something at the left hand side as well as the right hand side. And the element what I am going to add at the both the end is, so k plus 1 into k plus 2. That is k plus 1 into k plus 2. That is what the element I need to add. And so instead of writing all these things, I will just write the last part as k. So this is until k. So k plus 1 plus, I need to take one more element now, and so k plus 1, and now this is going to be k plus 1 is k plus 2. Now this should be equivalent to this statement by adding k plus 1 into k plus 2. Hence, I am just going to consider that statement over here, or let me write it over here itself. So 1 by 3 and k of k plus 1, k plus 2, and so plus k plus 1 into k plus 2. Now this is the statement what I am going to make. So now I am going to take k plus 1 into k plus 2 as the common factor, and so equals so k plus 1 and k plus 2, I am going to take it as a common factor, hence I am going to take k by 3 plus 1. Fine. So just check it out for this common factor. Fine. So having this, my next statement is I am going to make a cross multiplication over here, and I am going to say x k plus 1 and k plus 2 is multiplied with k plus 3 whole divided by 3. Fine. So now just taking 1 by 3, because everything is multiplied, so just take 1 by 3 over here, and I am going to have k plus 1 this part and k plus 2 the second part and the k plus 3 the third part. Hence, so now whenever I am going to have the statement, so this k plus 1 is replaced with k, and k plus 2 is replaced with n plus 1, and k plus 3 is replaced with n plus 2. So if you want, you can simplify this further, and you can say this as k plus 1, this is k plus 1 plus 1, and this is k plus 1 plus 2, so that you can easily understand what exactly I am trying to match with this. And due to this reason, this has been proved. This is proved. So as this is proved, so now S of n is going to be true for me. This is what exactly this problem is going to state with. Fine. I hope it's clear for you. Let's take one more example. Fine. And right now, let us take this example as the open statement S of n. So, which is going to state as 11 to the power of n plus 2, 11 to the power of n plus 2 plus 12 to the power of 2n plus 1. So, 12 to the power of 2n plus 1 is divisible by 133. This is the statement what I am going to make. So, this should be whatever the number I am going to end up with this, or the result I am going to end up with this. Now, this number, this whole number should be divisible by 133. That is multiplication or the multiple of 133. This is what exactly I am going to mean. So, for this case, so let me consider this with S of 1. I am going to have the S of 1 statement. So, where the S of 1 statement is going, I am going to replace this with 1, and this will stand as 11 to the power of 3, and I am going to have 12 to the power of, that is 1, that is 3, even this is going to be 3, so 11 to the power of 3 plus 12 to the power of 3. Now, what this is going to end with? This is going to end with, so 1331, so 11 into 11 is 1331. So, we need to do some calculation here. So, it's 1331. So, plus, so 12 cube is going to stand as 1728. And if I just sum up this, so just try to sum up this, it is going to end with, so 3059. And now just check out whether this is completely divisible by 133 or not. So, if I just check it out, so yes, it is divisible by 133 into 23 ends. So, 23 into, or let me write it over here, so it's equivalent to 23 into 133. Hence, this is divisible by 133. So, if you want, you can just check it out and verify. So, now this is verified that the given statement will hold good. It's going to be good for the element which is going to be divisible by 133. Hence, it divides the number by 133. So, this is what exactly the first statement is going to be. The next statement, where I am going to have the kth element, and so k plus 2 and 2k plus 1, assuming it to be true. So, we will just move on for the next element, which is going to be for k plus 1. So, s of k plus 1, s of k plus 1. So, which is going to be 11 to the power of k plus 3, because I replace with n with k plus 1, hence I am saying this as k plus 3. So, plus 12, 2 into k plus 1 and plus 1. This statement what is going to stand. So, let me simplify, let us go on simplifying this and check out whether this holds good or not. And so, 11 can be written now again as, so 11, so k plus 2 into 11. I am just splitting this out. So, as 11, k plus 2 into 11 and 12, I am going to have plus 12. So, 2k, I am going to have 2k plus 1. I am going to have 2k plus 1 into 2. I am going to split this as 12 to the power of 2. Now, just observe what exactly I am doing here. So, 12, so 2 into k plus 1 as the first component, 12 into 2 into 1, that is 12 square as the next component. Fine. So, having this, I am just going to move on further, where I am going to have this as, so 11 k plus 2 into 11 plus, so I am just going to have 12 into 12 as 144, and so 12, 2k plus 1 into 144. Fine. So, this is the number what I am going to end with. So, once this is I am going to have a number, I am going to have this number can be again written as, I'll just show you. So, 11 k plus 2 into 11 plus 12 2k plus 1 into, I'm going to write this statement as 11 plus 133, or even I can write this as 133 plus 11. So both are on the same. So now again this statement, so 11k plus 2 plus 12k plus or 2k plus 1. So 2k plus 1, I am going to put it as a common factor now. Let's take this as 11k plus 2 plus 2k plus 1 is going to be the common factor, so which should be multiplied by 11, because 11 is here and even the 11 is also over here. So plus again I need to have 12, so 2k plus 1, so multiplied with 133. I have been divided this in two parts. It is 12 2k plus 1 into 11. It is 12 2k plus 1 into 11. So 12 2k plus 1 into 133 with the addition. So with this statement, if you just observe, now this is going to be equivalent to the k statement. That is, so 11k plus 2 plus 12, 2 into k plus 1. Now this is going to be for s of k, so which stands as true, which is going to be standing as true, which is multiplied with 11. So plus I am going to have this entire statement as 12. So 2k plus 1 into 133. So now by having this statement, now the assumption what I made here, it was true, and anything multiplied with 133 and adding this up, even this is going to be true for me. Hence, so this is where I am going to say the statement has been proved, because so now this number will be divisible by 133. So proved. Hence, so now I can say hence, so S of n is true, or it has been proved. Now this is exactly how we are going to work with the statement with this particular problem. So please try out this particular problem. So if you understand this concept so clearly, fine. So now we'll just move on for the next type of problem. But before moving to the next type of problem, I'm just going to give one more form when I want to try to prove something using mathematical induction. And now whatever the form I'm going to give now this is going to be of the form an alternate form of a mathematical induction. Fine. Hence we are going to call this as mathematical induction alternate form. Hence alternate form of mathematical induction. This is what I am going to have, and I am going to try one problem with respect to this alternate form also. Fine. So now in this alternate form, so whenever a statement is made, I am going to check for some positive integers. That is, for some positive integers, for some positive integers, so just say it as n0, comma, n0 plus 1, n0 plus 2, so on, n0 plus p. So if I take some integer values, positive integer values, now I am going to prove it is going to be true. I am going to prove that the statement n of 0 is going to be true, and the statement n of 0 plus 1 is also going to be true, and s of n0 plus 2 will be true, so on. So s of n0 plus p will also be true now. Hence, so keeping this in mind, so for all this statement it's going to be true. I am going to derive now, or I am going to assume that now whatever the step we have made here, I am going to assume that all these cases are true. Hence, I am going to say, so s of S of k is true, S of k is going to be true, where S of k is going to be true, where so k is going to be greater than or equal to n naught plus p. So this hereafter all these are true, and hereafter whatever the k value I am going to take, which is going to be greater than or equal to the last integer what I have been tested it out. Fine. So this is going to be true, hence are true. So now this assumptions I am going to make now. So keeping this assumption in mind, I am going to say that S of k plus 1 is also true. Is also true. Hence, now just check it out. I am just going to take few integers, and check out with that integers the statement is going to be true. Hence, if it is true for all the cases what I am considering, remaining elements to be assumed to be true. Hence, S of k plus 1 is going to be also true. Now this is what assumptions we are going to make. So if you remember in the previous form what we were discussing until now, it has got 3 steps. So which usually we are going to state it as verify, assume and prove. Fine, the 3 steps what we had followed. Now this very first step usually we are going to call this as basis. And now this is going to be called as induction or induction step. So we are going to have the basis step and we are going to have the induction step. Now this is the 2 steps of course in mathematical induction, but now this is exactly how we have been divided in 2. So in that perspective, I am going to have this entire thing, whatever the proof I am making. Now this is going to be the basis step for me, and now this is going to be the induction. Step for me. Fine. Now this is an alternate form. So we'll just try to solve one problem with respect to this alternate form. Fine. And now just take this example, particular statement, what I'm going to make. So this is S of n, where the number what I'm going to take. So the number which is going to be greater than or equal to 24, whatever the number you're going to take now, you need to make sure that it's going to be greater than or equal to 24. So this number, whatever I'm going to take, so can be written as sum of fives, number of fives, and or number of sevens. Fine. Whatever number you're going to take. So this is how we are going to solve it. So to just check out this. So as in the alternate form, so first let us check out for S of n0. There's the very first value. Which is the very first value now? Now the very first value is not 1. If there was no such condition, then I would have picked n equals 1. But there is a number here, and the condition is the number should be greater or equal to 24, and the very first number is 24. Now don't try to prove for S of 1. I need to start from S of n0, and n0 is going to be 24, not 1 now. Hence I am going to have this as 24. I need to prove it for 24. Now can I write this 24 as the sum of 7s and 5? And now this I can write as 7 plus 7 plus 5 plus 5. Hence it's going to be true. So for n0 it's true. Let us take it for n0 plus 1. n0 plus 1. So 24 plus 1 is 25. This, can I now write this 25 using number of 7s and 5s? Hence, if I am going to use 5 5s, now this is going to solve my problem. Hence, this is true. This is also going to be true. Now just check out for n0 plus 2. Now this is going to be 26. Now can I write the 26 in the form of 7 and 5s? So you can just check it out. It's going to be 7 plus 7 plus 7 plus 5. then this is going to be true. And so further, you can stop at any point. You can stop at, so you can just check out with 27, you can just check out with 28. Now for all this case, it's going to be true. So when all this conditions is going to be true, so now we are going to say that it is true. It is true for S of k, where so k is going to be greater than or equal to, I have been stopping at this step, hence I am going to say greater or equal to n0 plus 2, and if you are going at this 27, and if you try to solve at 28 also, it's going to be plus 3 and plus 4. Even I can this as plus 4. It's going to be true for this case. So if it is true for this case, then let me put it over here. So then I am just going to have the statement as k plus 1. So which is true for k minus 4 plus 5. That is, I have been already used with the 4 numbers, hence I am separating with 4, and I am going to take the fifth element for k plus 1, hence I am going to take the fifth element and I am going to say it is going to be true. Hence it is true. And for this reason, so S of n is true. And so I am going to use the alternate form, so in mathematical induction, to prove whether the given statement is true or false. So with the same sense, you can just check out with the problem what I have given. Thank you.